Hello, today's video is a pre-lab lecture for the airbag lab. So the airbag lab is an experiment that takes part in 3 individual parts. Part 1 is where we're going to simulate the process of airbag inflation by working with a baseline chemical experiment that is designed to produce gas as a product. So if we think about an airbag, how an airbag deploys in a vehicle. When a vehicle goes in a head-on collision, there's a chemical reaction that occurs upon that collision that produces a gas quick enough in order to fill up the airbag vessel. And so if we think about this production for a real-life airbag, that gas production has to be extremely rapid, and it also has to be complete. So what complete means is that volume of whatever volume that your airbag is, that chemical reaction that produces the gas has to completely fill up that airbag. So you can think about the consequences if this chemical reaction was not rapid and not complete. So consider a front-on collision. If the chemical reaction was slow, your head would slam off the steering wheel before the time that all the gas has filled up that airbag. On the other side, if the reaction is not complete, if it doesn't have enough of a percent yield, if it doesn't fill up the entire airbag, then when you have that head-on collision, your head will go right through that airbag that's incompletely filled up, and again, the safety mechanism would not work. So we want to sort of take a look at a gas-producing chemical reaction, and we're going to try to optimize it in this experiment here in parts 2 and 3 to produce a chemical reaction that is both as rapid as possible and as complete, so having the highest percent yield as possible. So in part 1, we're going to be working with our baseline experiment, which is a combination of sodium bicarbonate solid with acetic acid, aqueous, to produce our carbon dioxide gas. So this is the gas production that we're going to be using to mimic the airbag reaction. And then also that's going to produce side products of sodium acetate, aqueous, and water. Okay, so this is just a simulation of the reaction. The true airbag reaction includes sodium azide to produce nitrogen gas. So that's a much faster and rapid reaction. But we're going to use this just sort of as a mimic reaction where we're producing a gas in a chemical equation. Okay, so part 1, we're going to be getting used to working with our apparatus here. And so the apparatus that we're going to be setting up is we're going to have an inverted graduated cylinder that's going to be totally filled with water. And then we're going to have a tube insert into that inverted graduated cylinder. And that tube is going to be connected to an Erlenmeyer flask that is going to be completely closed up. And once that solid sodium bicarbonate and the aqueous acetic acid combined together, that carbon dioxide is going to flow through that tube and displace the water out of the inverted graduated cylinder, and that displacement of water is going to end up giving you the amount of gas produced. And so we're going to observe the amount of time that it takes to produce the gas in this process, and we're going to observe the quantity of gas in volume that is produced. So in part 1, we're just going to be getting used to working with this experimental setup, and we're going to figure out the conditions for a baseline experiment. In part 2, we're going to do an R&D. You and your partner are going to work through R&D to optimize this reaction for increased speed and percent yield. So with this reaction, you're in this R&D step, you're going to have an opportunity to switch to a different type of acids, different types of carbonates, and different concentrations. And we'll go over those in lab. In part 3, then you're going to move on to our part 3 airbag simulation, where you're going to test this optimized reaction using a Ziploc bag. So you're going to scale up the reaction and you're going to mix them together and see how fast and how complete that you can fill up that Ziploc bag. So in parts 1 and 2, we're shooting for a 40.0 milliliter theoretical yield for carbon dioxide. So based on our desired amount of a 40 milliliter carbon dioxide theoretical yield, we must calculate the amount of each of our starting materials that we need to use in order to produce that amount of product. So here we're basically doing the limiting reagent sort of problem here, where we're working through a stoichiometry twice over, but we're doing it in the reverse direction. After knowing what the desired theoretical yield is in liters, we need to back calculate to see how much of our sodium bicarbonate and acetic acid that we need in each case. And so the way that we're going to convert here, based on our volume of CO2, if we convert that 40 milliliters into liters, that would be 0.0400 liters of CO2. We can use the ideal gas law, which I'm going to speak briefly about in the next slide, to convert that volume of gas into moles of gas. Then we can use our molar ratio based on our chemical equation here to convert to moles of our sodium bicarbonate, and then use our molar mass to get to our grams of sodium bicarbonate. We can also then start with our liters of carbon dioxide, use the ideal gas law to get to our moles of carbon dioxide, use our molar ratio to get the moles of our acetic acid, and the molarity of our aqueous starting solution to get to our volume of acetic acid needed. So those are two calculations that you'll need to work through prior to getting to lab to see how much starting material that you need. So let's speak for a moment about this ideal gas law. So the ideal gas law is PV equals nRT, where P is pressure in units of atmospheres, V is volume in units of liters, N is number of moles of gas, T is the temperature in Kelvin, and R is the ideal gas law constant, which is 0.082058 liters atmospheres over moles Kelvin. And so it's important to note that the units for each of these individual components of the ideal gas law are highly important. The equation only works if all of these individual parameters are in the units defined by the equation. So if you are given a pressure that is in millimeters of mercury or in pascals or kilopascals or bar or torr, you need to first use stoichiometry to convert those into units of atmosphere, which is required for our for these type of problems. If you have a volume that's in milliliters, you need to make sure you're put in liters. For moles, that's just a mole unit, so there's no unit conversion there. And temperature, if you get a unit in degrees Celsius, you need to add 273.15 to convert that into units of Kelvin. Okay, and so what are the key components of the ideal gas law? This allows us to convert between pressure, volume, number of moles, and temperature for any different type of gas. So there's nothing in this equation that identifies the identity of the specific gas. So whether you're dealing with carbon dioxide or nitrogen or hydrogen or oxygen, any type of gas that you're dealing with, this ideal gas law equation works the same. Okay, so for this specific lab, we need to use this ideal gas law to be able to convert between desired volume of CO2 and number of moles of CO2. So in order to do this using the ideal gas law, we first want to rearrange this equation to solve for moles. And then once we rearrange the equation to solve for moles, then we can then plug in all the values and use that as our conversion factor to go from our volume of 40 milliliters or 0.0400 liters, converting now to number of moles. And then once you have that conversion done, your stoichiometry carries on just as we did for a previous lab. Okay, that is all the pre-lab material we'll need. We'll go through our specifics of the experimental protocol in lab. All right, take care. Thank you.